Sir, you can start.
Okay.
You can continue,
So,
sir. Yeah.
so now I have completed till that thing. There are three classical types of atomic clock. One is hydrogen measure, then cesium and rubidium. And though there are many types of other atomic clock has been developed, but the three is the most popular and most commonly used atomic clock. They have a different its own merits and demerits. But about the accuracy and all this thing, I'll give a comparative charts very soon. What I would like to tell you that the cesium and the rubidium clock are mostly used by the GPS and GLONASS. Most of the GPS and GLONASS constellation, GLONASS satellites use cesium and rubidium clock, whereas the Galileo and Baidu, they use hydrogen maser and the rubidium clock. And so far my knowledge goes that rubidium clock is also used by NAVIC. I am not quite confident about the use of clock by QZSS. I do not have ready information, but I guess it is rubidium clock. So this is the what the different types of clock used. I'll little bit cut short the other slides and I directly go to the comparative chart. This is the first type of oscillator. First type of good cheap quartz oscillator was now available at within $10 to $100 with an accuracy at 10 to the power minus 6 and stability 10 to the power 11. Let us assume that stability is the how stable is the frequency source is that how accurate is the clock source is there. And accuracy means it has to be calibrated, so accuracy is much poorer, but stability is much good. High quality quartz oscillator is quite good. Again, the stability is poor, yeah, accuracy is poor, but stability is quite good as rubidium clock. Rubidium clock has a poorer accuracy, but better stability. Whereas in cesium clock, you can see 10 to the power minus 30 is the highest accuracy. That is why cesium is called the primary standard of time because its accuracy is quite high and stability is not bad, it's quite good. And hydrogen measure is also used more extensively in many cases better than cesium clock because it has a stability of 10 to the power minus 15, which is highly stable. But as because it has a inferior accuracy, so it is not used as a primary standard of time. Primary standard of time still remains cesium clock because it is the highest accuracy. Accuracy is important that when you start running, it will start at that frequency without any calibration and this thing. But in all other cases, that rubidium and hydrogen, you will have to have a beginning in the calibration with respect to cesium so that it becomes as good as a cesium clock. So these are the important thing I wanted to bring to your knowledge and other applications of different types of clock is given here. But you see that in all these cases, GNSS use rubidium, cesium, and hydrogen measure. And here I would like to talk about another important thing about the see whether that transference is there. Well, if it is not there, then here I would like to give a statement that these commercially available rubidium and commercially available cesium and commercially available hydrogen measure cannot be used as an clock in the for the satellite application. For example, in GNSS, if you would like to have a payload of rubidium, cesium, or hydrogen measure, it requires a special design. Why? Firstly, it will have a lot of vibration during the launch of the satellite, so it will have to stand that vibration. Secondly, while it will be in the launching period, then there will be environment is totally different of the whole payload. temperature, pressure, everything will be different. And another important thing is that while it is in operation in the orbit, there will be also different environment. So you'll have to manage those environment. The clock design should be same. Another important aspects of the clock design would be that it should consume minimum battery, minimum power, because there will be always a shortage of power while it is in operation in the orbit. And also it should have a minimum weight and minimum size so that it can go well inside the payload without increasing the weight much. So this commercial cesium clock doesn't consider all these things because it doesn't require, because otherwise this will increase the cost very high. But in the case of satellite mission, the cost is not important, but the other requirement is very important. So it is a special design of the rubidium cesium and atomic clock. So now the definition of the time. The time is that the revolution of the around solar axis is not used as a definition of the time is these days, because there is a variation of the period of revolution when the clock, better clock was discovered. So the at present, after that, when it was decided that time will be defined by the revolution of the earth around the sun, not its own axis. So that means that fraction of 1 by 31556925774 of the tropical year is 1 second, which is a very difficult to use. Then when cesium was found, then it was defined cesium as a primary standard of second. So, so this is a second is the duration of 9192631770 period of the radiation corresponding to transition between two hyperfine transition. Hyperfine level, I am not going to explain it right now because I do not have time. But this oscillator, commercial oscillator is available. There are many companies coming up, for example, Quartz oscillator, Kenco Incorporated, Chrono Technology, Shanghai Space Electronics, Orilla. There are many companies, but the many primary competitor is the Micro Semi Corporation. They are being largely used. Now, yes, I was looking for that photographs. These are the special photographs of the space qualified clocks. As I just now tell that it should have a small weight, volume, low power consumption, survive launch environment, that is shock, acceleration, vibration, environmental, that means vacuum, thermal cycling. These are all these things are specially designed for the satellite clock. Now, this is just for your information. High biggest clock in the world is that clock that has been by Arbaj Al Bhatt complex in Makkah. This is the large size. This is just for information. This is based on cesium atomic clock. Now, how the clock progress? I'll just give a summary. You see that it is 100 seconds per day. Accuracy was to for a long time. That means first Chinese clock, then cathedral clock, then first escapement clock, then spring-loaded clock. These were all within 100 nanoseconds. But then when pendulum came, this accuracy increased. It becomes 1 second per day. Then came the basic revolution came when there is a crystal oscillator was devised, and it was 100 microsecond per day, which is equivalent to rotation of the earth. And then came the first cesium clock, and then cesium clock commercial one, then cesium fountain, then optical clock. You can see there is a sharp increase during the year 1950 to till now. There is a sharp increase in accuracy. Before that, there was a very flat improvement, almost hardly any change till 1700 from the beginning. It means almost 700 years, hardly there was a change. Then from 18 to 1900, there was a slight movement because of the pendulum discovery and the different type of chronometers, and then came the quartz. There is a boom, that is the atomic clock era. Then there is a boom in the accuracy. Now, the question is that why atomic clock used in the because you require when you are talking about the accuracy of the 1 millisecond accuracy. For example, in the navigation, you are talking about the millimeter accuracy, then you require a range accuracy of the order of satellite range accuracy of the order of few centimeter. So otherwise you will not get the accuracy. And if it is few centimeters, then you require a clock to be very accurate. So only when the atomic clock was conceived, then people could thought of satellite navigation. So I'll not go to the local time and all these things because I will go switch over to the. You excuse me for that. Yeah, I'll change the slide for the next part of the talk. Let me switch over to that. Uh, uh, Excuse me for the change of my slide. Now, I'll go to the second part where I'll talk about time scale, time transfer method, concept of time transfer accuracy, accuracy limits, improving accuracy, and concluding remarks. This is how I have outlined. Let me quickly review what I was talking about. That the basic is the atomic clock. It's based on atoms, atomic structure, and the definition of time is now based on the cesium atomic clock. And there are this type of different type of commercial clocks available, and you have already given the review of the different performance of the different clock. Now, the how the different laboratories got into the atomic clock. Every clock, the old laboratories, for example, including NPL, started with a quartz crystal oscillator. So that is Asian ring crystal oscillator. That was the first primary standard for the timekeeping. Then first atomic clock NPL purchased in 1974. It was a news that many people wanted to see how atomic clock looked like. When they came to the lab, they were very much disheartened because it was a 19 edge rack system, uh, a simple black box. They couldn't see anything like atom moving or something like that. But anyway, this accuracy was very important. Now NPL has more than five. I know at present they have 7, 8 atomic clocks, including Heisenberg and Maser, and also Fountain. Now, thing is that why I am showing all these things. For example, in NBS, there are more than 150 atomic clocks scattered in different places. Now, thing is that of all these clocks, compete with each other in accuracy and stability. Everybody has a very good accuracy and stability. Now, so when I am talking about the universal time and all this thing, does it depend on a particular clock? Any one of them is very good and can be reference. The question comes, which one will be the reference? It is a big decision. So any one of it can be reference. Now, if I say that NPL clock is a reference, then USA say, why not my clock is a reference? And PTB will say, Germany will say, why not my clock is a reference? So, so people started thinking how to do this because actual performance shows that the different clocks, the behavior is like this. So this is in terms of nanosecond. So over the years, okay. So they are well within limit of the specification. Then why I should drop one of the clock and other as a reference? This is not fair. So what is that? All clocks perform equally good. Can you term one of them as a reference? No. So what is the solution? Solution is that let us make an average of all the clocks and make a more uniform time scale. So now this is a very difficult thing because all clocks scattered all over the world are not at the same place. So you cannot put all 400 clocks side by side and make a comparison. This is not possible. So So the problem is all clocks are far scattered geographically. Now we'll have to link them remotely. So only solution is the GPS. Link them with GPS as a common link by comparison. So each clock at different parts of the world is compared with the local clock, and that data is being sent to a particular central place, BIPM, and BIPM generates the average time scale. And that average time scale is a paper scale. Please note, there is no a particular crash which is the average of all the clock, but it is a paper scale. How do you realize that paper scale in practice? BIPM says that with respect to particular average time scale in paper, and they will correlate the time of a particular lab with respect to and see that your clock with respect to my paper clock is off by 1 nanosecond. So that is how you have a realization of the average time scale. Now, what BIPM temperature generates a paper scale, which is the international standard of time scale, not a particular one clock. It is an average of all clocks, and I know that how much I'm off from the particular paper scale, which is the best average of all clocks. I know exactly how much it is off from that scale, and that is how I know that this is my standard with respect to a international standard. So this is all coordinated by BIPM. That is, BIPM is so important and the timing activities. Now, these what are the participating clock? There are more than 80 laboratories contribute, and each laboratory has many clocks. For example, NPL has 7 or 8 clocks. So participating clock is more than 450. At present, it has come back to almost 800 clocks contributing to that. So the time scale that we get as an international time as present, which is called UTC, Coordinated Universal Time, is based on 800 clocks. So it is much better than a single reference clock. So this is the basis of civil time, and this is 24-hour standard is kept using highly precise atomic clock combined with the Earth's rotation. Now the UTC, that means Universal Coordinate Time, is a clock based on a cesium atomic clock or other hydrogen measure or rubidium clock. It has no correlation with the rotation of the Earth. But as because we are human being, we'll have to have some correlation with the rotation of the Earth. So, so there is a time which based on the rotation of the Earth is the UT1. So there should be a correlation between UT1 and UT1 because that is important. So, so UT1 is being observed by the astronomical observatory of the world, the Earth rotation. They keep an eye on it. When and they always want that UT1 and UTC should not exceed by zero point 0.9 seconds. That is the understanding as of today. So, moment this it will exceed chance of exceeding zero point 0.9 second, then we'll give a jump to UTC so that it goes near to UT1. So that is the arrangement is present done, and that jump is called leap second given to UTC. So now with the GPS time doesn't give jump to the clock. There is a continuous time, but they have given jump only once in the beginning, and so they are continuously running at present. So I'll give you. Let me see whether okay. Let me come to that. So I'll come to that how the other time scale of the different labs, different constellation. I'll come to that. I have a different slides for that. But anyway, we give a leap seconds to have UTC in line with the UT1 that is based on the Earth rotation. So this is what is the status of the clock today. Today, UTAI means if you do not give a jump, and UTC which keep on giving jump, we have given 37 jumps as of today. So last leap second was given. It is a very old slide. Actually, last leap second was given way back. I don't know whether this is right. It is not that old. It was in 20. Uh, Let me see whether I have that figure. I'll correct it to my knowledge. So anyway, These days it is so much good that you do not need to give a leap second. It is almost same. But you can see there is a leap second time to time and this going on. So anyway, at present the understanding is that as because the leap second is very infrequent, you may have to wait 2 3 years to give a leap second. So that duration of zero point 0.9 is being thought about so that we can get rid of the leap second. So now the clock status of the contributing laboratory. So as I told you that what is the difference between the UTC and time scale of NPLI. So you can see that we are trying to give it as close as possible, that 1.6 nanosecond, 1.2 nanosecond, all these things. That happens with the all other laboratory. So we have a plot of this. This is how the different clocks vary with respect to UTC time, different laboratories. And you can see they are well within 3 to 4 nanosecond with respect to standard time. But we know this value exactly. Suppose India NPL, I know NPL what is the exact difference between UTC at that time. So this value is correctly known. This is only a variation how long it is varied. So now question is that this is how time scale is used and how they even the all the GPS and GLONASS and the Baidu and Galileo time is maintained. They are controlled from the ground station, and the ground station control the atomic time of the clock, all the satellites orbiting in the sky. So because this is the heart of the all navigation system, so your clock time should be very very precisely maintained and monitored. Because if we do not know, and because not only that, all the clocks in the satellite constellation, whether it is Galileo, they should be correlated. We must know what is this value. Otherwise, our now the concept is that you use the navigation system all as a one constellation. Suppose it's a combined GPS, GLONASS, Galileo, all satellites taken common, and you can get a solution. It is possible because all the timing system and coordinate system should be strongly correlated. Otherwise, you will not be able to get a solution properly, because then another uncertainty will come in. Then you will require a n number of uncertainty unknown, and you will have to solve a very complicated equation. So the synchronization and coordination of the time scale and the position scale should be well known in advance, and that is how time is maintained. Loss of synchronization inedible. That is what now why we require a dissemination. There are three phases of time transfer. What was? Let me give you a little story. What happened earlier, before the GPS? Before GPS, there was a church bell used to gong and give you a time. That is very primitive, Jed. And the time ball used to drop, and the factory siren. Those are the time system. That is well before 1920. But in 1920, the whole beginning of the new era, transmission of time signal. That time already the good clocks has come into the market, and people know how to transmit signal through electromagnetic waves, and that is then the new era started. That is then Lorentz started, Omega started, HF technique started, internet. But the actual revolution in the navigation came when the satellite Sputnik was launched, and people got to know what satellite is, and they developed this technology very rapidly, and now that is how the GNSS has come into the market at present, has seen the light of the day. Now, the first type of you have been already given a lot of exposure on what is GNSS. It was poured on our GPS, and this is a one-way ranging system. So now I'm not going to say that, but this is one important you have not been talked about, and most probably none of them speaker has not covered, I guess, that the clock that is on the satellite has, when it is in orbit, there are two types of effect on it. One is that second order Doppler effect, one is the gravitational percentile. Because the clock, while it is in orbit, it has a motion, and also it is at a totally different gravitational potential than on the surface of the earth. So as a result, there will be the frequency will be different from when you launch here, and before the launch the frequency what you have set, it will be totally different when it is in orbit, because of these two effect. So you'll have to compensate that. So it has been calculated that when GPS orbits at 26,562 kilometers from the center of the earth, and base frequency is 10 to the earth 10.23 megahertz, base frequency may be anything. So it will have to you'll have the frequency will change enormously. As a result, unless you compensate at the ground, suppose if the frequency increases by some amount 10 to the power 10, so unless it detune it by 10 to the power 10 at the before launch, so that when it will be launched it is in orbit, it will take the exact the frequency you are aiming at. So that is one important thing of the relative relativity is done, that it was detuned. So all the frequency of the base oscillator, whatever may be the things, has to be detuned before launch to a particular amount, so that when it is in orbit, it gets the exactly same base frequency it is designed for. For example, for the GPS, it is 10.23, but before launch, it is 10.229999954 megahertz, and then it was launched. So this is very important thing. Okay. Now, GPS observation equation, you know how it works. All of you know that observation equation is that, which is I would like to concentrate because that is important for timing. So you see that apart from this true range, this rho, it has a difference between the satellite clock with the reference and also the receiver clock with the reference. There is a time offset. So if we ignore the reference time, then I must know the receiver minus satellite time. So because it is cancelled reference time. So I'll have to know the difference between the satellite time and the receiver time. So this is one unknown parameter, and other unknown parameter is the receiver position through which you will get the true range. So this equation is important. And apart from that, there are other factors that contribute to the error is the ionospheric error, tropospheric error, and the other measurement error like multipath, receiver noise, and all those things. So to get a full accuracy of the GPS system or GNSS system, firstly, we'll have to know that what is the position of the satellite. Position of satellite, though it is transmitted, but it is based on the satellite ephemeris that is available from the receiver navigation message, who received navigation message, and the navigation message, whatever is transmitted, is not very accurate. So that will introduce some error. And also, the clock in the satellite is normally remotely controlled by the respective organization like USA by USNO, European Union control the Galileo clock, Chinese timing system control the Baidu. Similarly, the things. Excuse me. so 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 we'll have to take care of this error. Let me look at this error. The in terms of the range error, satellite clock gives 2.1 error, 1 sigma error. Ephemeris time, that is satellite clock, there is ephemeris time where the prediction of the satellite position is 2.1 error. The highest error is the ionospheric error. Tropospheric is zero point 0.7. Multipath is 1.4 and reservoir noise is zero point 0.5. So this all is a 1 sigma error contribute to the inaccuracy of the either position or time. Now, this when it is all added in a uh, root means of the uh, sum of the square, so this becomes 5.3. This is RSS. That means root of sum of the squares of all term because it is a 1 sigma error. So this becomes 5.3. So if you take one observation, then you will get a position as 5.3 meter, and that equivalent to uh, 35 nanoseconds for the timing error. So, so if you receive a satellite clock, or if you receive a time from the satellite receiver, you will get an error automatically of 35 nanosecond or a position error of roughly 5.3 meter. But the actual practical situation is not that bad because when you make an average and all this thing, so many errors will get reduced and you will get roughly at present what you are normally getting in different places. Now, one have made much better than this. So now let us see. One is that you can get a direct access of time from the GNSS receiver without making any correction. And in that case, you will get roughly 30 nanosecond type of error by that. But there is another way you can do it is the GNSS DO. That means GNSS disciplined oscillator. It is of course same as the direct access, but the difference is that it has a disciplined oscillator. That means it has a phase lock system which always lock to the GNSS system. And if GNSS system fails, it will give a free running system. And a free running system, what is the performance is that the RAID is the free running system, and this is when it is locked. These days, this servo lock is so intelligent. It's remember the history. So if the satellite is lost or the GNSS signal is lost for a short time, then it will, to a great extent, maintain the same frequency, same time as it is without, as if it is there is a GNS oscillator. But after some time, it will deviate a lock. For example, this is a free running and it deviates along after certain time. Till certain time it is within the range. Then after certain time it will free. That is why GNSS DO discipline oscillator is because popular because everybody cannot has a atomic clock, afford an atomic clock. So you have a crystal oscillator which serves as a GNSS locked oscillator for a long time, even if it is not there.
Sir, you can take a break for around after 2 3 minutes. You can, whenever convenient, you can take a break for 10 minutes once again.
Then
Then there will be 30 minute session. You can finish up, and then if there is any question, a few questions has already been put
no,
into
then
the.
let me quickly finish up the talk.
Okay, okay, but as you wish, sir.
Okay, let me finish up the talk within 10 minutes. Then I'll go take up the question.
Okay.
Okay. So now I'll quickly go to that how the accuracy is improved. So accuracy improve as I told that those uh, parameters has to be reduced. These these parameters has to be reduced cut short, and we'll have to see how we can do that. The one way is that you use a multi instead of a dual frequency timing receiver, which is a special receiver which gets the time through one particular satellite because it has only one unknown and a predetermined static position. So you can get the timing solution from a one satellite receiving one satellite. If you have a multi-channel, multi-frequency, then with the two-channel, with the multi-frequency, with a multi-satellite, then you will have a for each satellite one solution of the time. So this is the type of receiver we are using for that. It is available in the market. Let me quickly show that what is the type of correction we can make. So the thing is that this is the format in which this is like Rhinex. It is a easily compatible format, is a CGTTTS format. So it is available in the common for the all receivers so that you can exchange the data. So one is that improving the accuracy is that you go in a common view mode. The common view mode is also used indirectly in a positioning also, relative positioning. So in a common view mode, so you get the time from a single satellite and same satellite used at the other end, and then you make a difference of these two, then you can get the difference between the two oscillator. The GPS being a common, so it get cancelled. As a result, many of the parameters get cancelled. I'll show you. So the satellite clock is get cancelled because you are saying the same satellite, so the clock of the satellite error is totally cancelled. And as because you are same satellite, you are saying that uh, coordinates will be almost same, but as because the range is different, so it will be partially cancelled, it will not be totally cancelled. And if it is a short bit line, ionosphere will be greatly cancelled, troposphere multipath will remain. Now if it is all in view is important in the sense that in a common view mode, you may not be always many satellites in common view. As a result, you will not be utilize all the satellite. But in a all in view, utilize all the satellite and make a difference average of time solution. Here is the average of solution. Then make a difference. Then you can say what is the advantage. You are not getting any advantage out of it. Only you have a many satellites and you have better average. Yes, you are right. So only thing is that receiver noise will get reduced. But how you to improve upon that? Yeah, you might have heard of the in all in view. What we'll do? You have suppose 8 satellites at the same time. So you have a at this MJD, you at the same time you have 8 satellites. You get a average and you get a this value. But what is the advantage of it? Advantage of it that if you have a IGS network, then you will get the highest quality of the data of the products. For example, you get a better positioning, satellite position estimate, and a better satellite clock estimate. So these two are cancelled. So as a result, and another thing is that, as you know, that now most of the receiver is a dual frequency receiver, modern receiver. So if you have a two frequency, the two frequencies simultaneously can be used to eliminate the ionospheric error. So as a result, ionospheric error is also eliminated by this, and it is coupled with the all-in view. Then you have a many of these. For example, the satellite clock error will be reduced, ephemeris clock error will be reduced, and the multipath will be also reduced. Now the thing is that concept of the carrier phase is a very important thing because it is a carrier frequencies wavelength is much shorter than the code wavelength. Now, as a result, the shorter the wavelength, better is the noise accuracy and better is the multipath rejection is better. So, having advantage of these two position, we have a new technique called PPP. The why PPP position is that what you do is that it is a dual frequency receiver where we not only make the ionospheric correction same, we use the IGS product so that we get the ephemeris of the coordinates, coordinates of the satellite, and the satellite clock error. These are all very precise, so it can be used without any, almost without any error. And as because we are using the carrier phase, then we have a better resolution, as I explained just now, that it will have a better multipath rejection, and also it will have a better resolution and noise less. So as a result, the PPP is a very good technique. The how it can be operated, you operate a receiver in a Rhinex, store the data in a Rhinex format, and use a standard chop set. This is available on the online is that using Atomium, Enercan, JPL, Barneys. These are the all available. You can use it to get the PPP solution. Now, what PPP solution has an advantage that it has a satellite clock almost eliminated, ephemeris time is error is eliminated, ionospheric error is eliminated, and troposphere is eliminated. Multipath, because of the you are using the carrier phase arrangements, the multipath is greatly reduced, and because of the high average time, averaging of the more satellite, you will get receiver noise almost eliminated. So this is the best available technique for the PPP. I'll not talk about this. So now at present we have very large number of satellites. This is at Burdwan University. The 48 visible satellites are there, whereas in Washington, the 40 satellites is visible. Now, the reasons of less number of satellites in Washington, most probably somebody explained it. I'll explain it then later because India is in a better position. They have an additional constellation of NAVIC and the QGNSS. So now to summarize it, that we have different type of time transfer techniques, that LA broadcast, telephone line, NTP. I didn't have time to detail on it, but they are only in the millisecond order. First breakthrough in time transfer is the GNSS time broadcast 20 to 50 nanosecond. Then GNSS all in view 3 nanosecond, and GNSS PP is now picosecond order, 500 picosecond order. And two-way time transfer is a competing value, but I am not talking about that. But GNSS is already reached 500 picoseconds, and uh, IPPP is another technique GNSS where uh, ambiguity integer is resolved. So you can get little better than 500 millisecond, which is competing with 300 picosecond. So this is how it stands at present for the time transfer. So you can go up to very comfortably sub nanosecond level with the GNSS technique. So this is where it stand. Now the question that may come, I am ready to answer for that. I am not able to cover it right now. Rather, I have deliberately put it off. I may talk about its application. Why do you require sub nanosecond, sub pic nanosecond order? What is the applications? Why do you like to have it? So even that is true for the positioning also. So that will be by the next speakers. Few speaker will talk about that. What is scientific application? What is common view societal applications? I'll end up this talk with this because I have many other things to say. Only thing is that I'll just summary slides is that this is how the timekeeping improved, and this is how time transfer improved. Rather, time transfer has a big go when the GNSS came into the market, and we have improved from 200 nanoseconds to 300 picoseconds. Optical fiber I have not talked about. This is not part of GNSS, and optical clock is also not used in the constellation yet. Now this is another part of the time and frequency activities. So with this, I'll conclude my talk, and any discussion on this is welcome. Thank you.
Thank you very much, Dr. P Banerjee, for uh, taking such effort to communicate to our participants, starting from the very basics to the very advanced techniques of time transfer. So what we will do now, we will stop for 1 second for 10 minutes, and at 21:10, we will start a question answer session. A few questions has already been typed in. If you have any more questions, please type in, or you can ask directly.
You will
So
you'll start at 9:20.
no, 9:10, sir. 9:10
9.
to 9:30, maybe 15, 20 minutes session.
Okay, okay. 9:10.